right, this is a video over some questions from sections 2.3 and 2.4 this week. So just a few of the WebAssign similar types. This first one says 3 molecules of type A and 3 of type B and 3 of type C and 3 of type D are to be linked together to form a chain molecule. Here's some examples of what that could look like. A, B, C, D, A, B, C, D, A, B, C, D, B, C, D, D, A, 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 B, D, B, C, C. So notice there are going to be a lot of possibilities for this specific string or chain molecule. So it says, how many such chain molecules are there? Now, the hint here is actually having you think about if we could tell the difference between the A's, B's, C's, and D's, which we technically can't because they don't have subscripts on them. They're just A, B, C, and D. But if you could tell the difference, then you would know that you have 12, that would be 12 total different, distinct items. So essentially, if they were distinguishable, then lining up a chain molecule would be 12 times 11 times 10 times 9. You just, every time you put a choice, you have one less choice for the next one. And we call that 12 factorial. But because they're not, if you, so for example, if you had, and this is a smaller example, if I had A1, A2, and A3, let's say I had just those 3. Let's try not to do a full chain, but let's just look at just the difference when we look at a single variable going from being distinguishable to non-distinguishable. So if we had this, we know that this is also different. And A3, A1, A2 is different. A3, A2, A1 is different. We could also have A2 starting off with then A3 and A1, just thinking through the different possibilities. And we could have A1, A3, A2. And I know that there are 6 possibilities because this is 3 distinct items, so that'd be 3 times 2 times 1, or 3 factorial. So if they're distinguishable, we would see 6 outcomes here. But if they're not distinguishable, in other words, what if they were just all just A? There's no difference between AAA and AAA. It's the exact same thing. So what we'll find is that that's just one outcome. Well, how are those two things related? And this is permutations of what we call duplicated elements. That's what this really is. So if you look at this, we know that we went from 6 outcomes down to 1. Well, that was 3 factorial for the 3 distinguishable items. And we divide that by the number of repeated elements. So for this one, so since there are 3 different repeated A's, we also divide by that factorial. This bottom part, they won't always match here. You'll see that in our example because we have a lot more repeating elements going on. But this is the division for the number of duplicated distinguishables. Okay, I can't really write that in there, but you heard it on the video. I'll try to rewrite that before I post the PDF. So for here, this is just going to end up being 6 over 6, which equals the 1 that we expected here. So I kind of wanted to do a simpler example so I could show you what we're doing here. So we have 12 factorial as if all of the different A, B, C's, and D's were all distinguishable. So like A1, A2, A3, B1, B2, B3, all of that. Then we need to divide by the number of duplicated elements in each group. So there would be 3 factorial, and that's because of the different arrangements you get for each of those. So that's 3 factorial for the A's, 3 factorial for the B's, 3 factorial for all the duplicated C's, and 3 factorial for the duplicated D's. So because we can't tell the difference, we need to divide all this out. Now, if you type this in on your calculator, you'll probably want to put a parentheses around this bottom part, but it essentially works out to, I believe it's 376,000 plus some change. Let me work it out again. So 12 factorial divided by, essentially that's 3 factorial is 6. So that's going to be divided by 6 to the 4th, because there are 4 of those. It's 369,600. So 369,600. So that's how many non-distinguishable chain molecules there would be, because in terms of A, B, C, and D being, you can't tell the difference between one A and another one. So that is, we are able to distinguish between A's, B's, and C's and D's, but not between the different A's, the different B's, different C's, and different D's. Okay, so the second one here, it has to do with grouping them. So we say, suppose that a chain molecule of the type described above is randomly selected, and we want to know what is the probability. So remember, probability has to do with desired over total outcomes. So we want to know what is the probability that all 3 molecules of each type end up next to one another, such as BBB, AAA, DDD, CCC. Round your answer to 8 decimal places. Well, this is a very specific arrangement, okay? What the big idea here is that you really only have 4 slots to fill. Whereas before we thought of kind of having 12 slots, and that's how we got this distinguishable 12 factorial. We are going to be able to tell the difference between a block of B's and a block of A's, but essentially we're blocking 3 letters together at a time. So the big question becomes, in what order do we choose these specific blocks? Well, we have 4 choices for the first one, because you could either be all B's, all A's, all D's, or all C's. You have 3 choices for the second one, 2 choices for the third blank, and then whatever block of 3 molecules chained together for the letters in the same kind, that would just be the last one. So that is going to be 24 for our desired. So the probability that we have the all 3 molecules of each type next to each other is going to be the desired outcome, which is this 24, over the total number of chain molecules that we had, which is 369,600. And we're going to divide that and round it up to 8 decimal places. And that's because it is a super tiny number. So it's going to be 0.00004 zeros, and then a 6494. So it'd be very rare for that to occur. Almost impossible. Not technically impossible, but close. It's almost 0. Okay, so let's look at number 2. This accompanying table gives information on the types of coffee selected by someone purchasing a single cup at a particular airport kiosk. So we have different sizes, small, medium, and large, and we have regular or decaf. And we were given the percentages in each of these. When I'm given a table like this, I like to go ahead and get the totals of everything. So the total number of smalls were 42%, medium was 30%, large was 28%. If you do your row, you can get your regulars. So that is, let's see, 22 and 20 would be 42 plus 18 is going to be 60%. And then this is 40%. And you'll notice, since these were written as percentages, this will be a total of 100%, either row or column summing. So these are just a nice way to help you get the probability attachment here. So we want to know, what is the probability that an individual purchased a small cup, and we want to enter it in decimal form. Well, we already know that because we have the total for small cups. So it's going to be 0.42. What is the probability that the individual purchased a cup of decaf? So that would be this row right here. So 40% or 0.40. If we learn that the selected individual purchased a small cup, what now is the probability that he or she chose decaf coffee? Now, this is a conditional probability because we've reduced the total sample to just the small cups. So we know that they have a small cup. So the way we write that is the probability now that we want to know, are they going to get decaf? And this is the symbol for given, which means we already know something about our choice. That we have a small cup. So when you're doing one of these, there's a formula for conditional probability. It is reduce yourself to the probability of the sample restriction, which is the small cup. We know we already have just a small cup in our hand. And then on the top, it's the intersection. You are small already, but you're also decaf. So small, intersect, decaf. So when we look at the table up here, the probability of having a small is 0.42. The probability being small and decaf is where those overlap. So the column and the row. So that would be 0.20. So we want to divide 0.20 by 0.42, and that comes out to 3 decimal places. They asked us to round 0.476. And then we were asked, how would we interpret this probability? Now you have, I don't have this here since I saved this as a PDF, but the options here, this is the probability of people who chose A, and then it had the sizes. So this was a small cup, or sorry, not small. This was the decaf, because the given that is the small. So yeah, it was decaf or regular for this blank. So they chose a decaf cup, given that they had already chosen a small cup. Okay. Now let's think about that differently. If we learned that the selected individual had purchased decaf, what is the probability that it was small? So this is the conditional probability the opposite way. So we want to know if I already know that it's decaf, so that's why that comes in the second condition part. So small given decaf. This time it's going to be the probability of decaf in the denominator and the probability of, again, the intersection in the numerator, because you have to be both to meet the numerator or desired condition. So for decaf, back up in the chart, the total number of decafs was 40%. So that would be 0.4. And small and decaf is still the same intersection that it was in this previous part. The difference is we restricted to a different subset in the denominator. So this is actually 0.5, which is why it says just round to 1 decimal place. So how does this compare to the corresponding unconditional probability of part A? Which, let's see, A, let's scroll back up. So the probability of small cup was 42, probability of decaf was 40. If we want to talk about this, the probability is greater than the unconditional probability of selecting just a small, because that was in the 0.42 range, I believe. Yeah, 0.42 was for small. So if we already know that we have a decaf in our hand, we're actually more likely for it to be a small cup than when we just said we don't know anything about it. So this is greater than. Okay, let's look at the third one. So this says, consider randomly selecting a student at a large university. Let A be the event that the selected student has a Visa card. Let B be the analogous event that they have a MasterCard. And let C be the event that the selected student has an American Express card. They gave us some probabilities. We have the individual single probabilities. We have some intersections of the two different groups, MasterCard Visa, MasterCard American Express, Visa and American Express. We also know the probability of the intersection of having all three. So again, when I'm dealing with something that has 3 sets, and I'm going to do my scratch work down here for this one, just because I don't have enough room to draw it anywhere else. I like to draw my Venn diagram out, especially if they've given me all those probabilities. And I'll be really careful this time to not make a computational error I did in the last video. Sorry about that. So we know that 0.08 is the intersection of all 3. So 0.08 goes right there in the middle. Sorry if that's hard to read. Let's make that a little bigger. So go back to drawing those circles a little bit larger. And I'm going to name these just like they did. They're A, B, and C, but I'm going to write myself a little memo over here that A is a Visa, B is a MasterCard, and C is an American Express, just to help myself with how they ask the questions to make sure I can tie those letters back to that. So let's put in at 0.08 in the middle. And then we start looking at our intersections of two items. So B and C overlap makes 10. Well, remember that's this entire kind of eyeball here. So 10 minus the 0.08 we already have in this dead center is going to leave me with 0.02. And then we have A and C, which is this portion over here, this little, I always call it an eyeball because it looks like a pupil and the whites of the eye. But that's 13 and this is already 8. So this has to be 0.05. For A and B, it's 0.30. So we already have 0.08. So that's going to be 0.22. Our A has to add up to 0.6. So we have 35. So that means that we're going to have 25 left over in this portion. Our B has to add up to 0.4. So we have 30 plus 2, that'd be 32. So that leaves me with 0.08. And then down here, C was 0.2. So the whole circle C. So that's 10, 15. So that's going to leave me with 0.05. Now, very carefully, I'm going to add up all of those interior pieces of my Venn diagram, and we're going to subtract it from 1 to figure out what's in the outside, which is students who don't have any of these cards. So we're going to subtract 0.25 from 1, minus 0.22, minus 0.08, minus another 0.08, minus 0.02, minus 0.05, minus one more 0.05. And that comes up with a leftover amount of 0.25. There's all of my probabilities. So let's answer the questions. What is the probability that the selected student has at least one of the 3 types? That means 1 or 2 or 3. Essentially, we're adding up all of the interior pieces, which we already know that's going to be 0.75 because the opposite would be outside here, which is 0.25. So one way to do it is to add everything up that was in the circles, or we could just say 1 minus the part that were no cards, or at least none of the 3 that they listed for us. So that's going to be 0.75. What is the probability that the selected student has both a Visa and a MasterCard, but not American Express? So let's use some of our set notation information here. So both a Visa and a MasterCard would be A intersect B. Think of that as a group. They have both, but not, which is also an intersection, American Express, but we're doing not C. So when we look at this setup, we're looking at, okay, the intersection of A and B. See if I can use a different color. I'm just going to put dots of different colors and then I'll probably erase these. The intersection of A and B is this 0.22 and this 0.08. That's the intersection of A and B. Not C, I'm going to use, let's say, purple. Not B is everything outside of B. So that's going to be, or not C, sorry, I read it backwards, not C. So not C would be this 0.25, this 0.25 up here, the 0.22, and the 0.08. Now, because we're connecting those with an intersection, we only want the place where we have both dots. So that's going to be the 0.22. Because that's where they would overlap. And I am going to erase some of those little dots because that makes it busy. Oops. That was not 25. See if I can. That was 22. And I'll fix those as well. Okay, so this was 0.05 and 0.08. Okay. Now we want to calculate some conditional probabilities. We want to do probability of B given A. That's going to be, we know A, so that's going in the bottom, and we want the intersection in the top. Well, B intersect A was 0.30. over all of A, which is up here, which is 0.6. So that's going to be 0.5. And they didn't say it had to be rounded to 2 decimal places, but I will just because we have been. And then probability of A given B is probability of B on the bottom and still the intersection on the top. So that's still going to be 0.30 on the top, but the probability of B was 0.4. So this is going to divide to 0.75. Okay, let's look at the next part about this one. It says interpret those conditional probabilities. So we want to make sure we're writing a statement correctly about both of them. So let's see. B given A is probability the student has a MasterCard given that they have a Visa. This is why I wrote this in. B is MasterCard and A is Visa. So this is not correctly written because we would say this is MasterCard given Visa. So this is saying Visa given MasterCard. So we want the one that is reversed. Yeah. This is the probability that the student is has a MasterCard given that they already have a Visa. So that is one of them. Probability of A given B is the probability that we have a Visa given that we already know we have a MasterCard. So that's going to be this one. Okay. And then if we learn that the selected student has an American Express card, what is the probability that she or he also has both a Visa and a MasterCard? So this is a little bit of a combination one. So we want to know the probability of, we're going to be given the American Express, so that's set C, but after we know that, they also have both Visa and MasterCard. So that's A intersect B. So for this one, if you write your formula, we know we have an American Express card, but we intersect this group with this one. So that ends up being the intersection of all three. So the intersection of all three was 0.08. Having been in group C was, let's see, that's 10 and 10, so that's 20, so 0.20. And that divides to 0.4. So this one would be 40% or 0.40. And then I believe there's one more in this one. Yep. Given that the selected student has an American Express card, what is the probability that he or she has at least one of the two other cards? Okay. And I just lost connectivity. There we go. Let me erase that. My mouse was not showing up on my screen for a second. So for this one, we're writing it as, we still know that we have American Express. So given American Express, which was C, but it's at least one. That means one or the other or both. That's a union of the other two. So when you do a union, you add up all of the things in circle A or B, but we're gonna have to also look at this a little bit carefully. So this is probability of C on the bottom still, but on the top, it's the probability of A union B intersected with C. So I am writing that one with the parentheses because you need to take the union first before you intersect it. Since the other one was all intersections, it ended up just being take the intersection of all three. So let's go up and look at our picture. A union B is going to be, let's see, I'm going to write this down here. Let me add those up. So it's 0.25 plus 0.22 plus 0.08 plus the 0.05 plus the 0.08 plus the 0.02. Just so we're aware, that's 70%. So there's 70% in A unioned with B, okay? Now, that's not our final answer for that numerator though, because we're intersecting it with C. So let's actually, I'm gonna highlight or use a different color again. So A union B is all the ones I'm underlining. We're trying to intersect that with just the ones that are in C. So C is here, 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 and here. So it looks like these three in the middle, that's going to be our places where the union of A and B is going to intersect with circle C. So that ended up being 0.15. It was the 0.08 plus the 0.02 plus the 0.05. That was the group that was in the middle there, over 0.2, or 0.15 divided by 0.2, which is 0.75. Now, it's just a coincidence that 75% popped up a lot of times is because these had nice numbers. That's why that happened. So let's talk about our next one. So this is something that is covered in, actually, I believe, section 2.4. Yeah, this is kind of I believe everything else up to that point was well, no, the last one was 2.4 as well. But the first one was a 2.3, and then 2.4, 2.4, 2.4. But at the end of 2.4, there's a theorem called Bayes' theorem. And Bayes' theorem is one that we use when we're looking for probabilities posterior. That's what they're called. They're before probabilities when we have the kind of end result answer. So it's a little trickier. There's a formula for that. I'll write it down when we do this first one, but one of the best things that I always do when I teach this in Math 135, when we see Bayes' theorem there, that's finite math, is I try to start with an easy one and draw out a tree diagram. So I want to do that first, and I'm going to do it kind of, because I'll have to do it over here on the side right here. But this kind of helps you see why we need to use Bayes' theorem when we get to part B. We can actually get part A pretty easily using the tree diagram as well. But the reason we use it for these conditional probabilities is because we don't have a direct way of calculating it. So that's why I want to show you this visually. So if you look at it, it says the reviews editor for a certain scientific journal decides whether the review for any particular book should be short, medium, or long. Data on recent reviews indicate that 50% of them are short, 30% are medium, and the other 20% are long. Reviews are submitted in either one of two formats, Word or LaTeX or LaTeX, depending on how you pronounce that. Different people I've heard do it different ways. But for short reviews, 70% are in Word. So notice this is a conditional probability. We already know it's a short review, and 70% of those are in Word. Whereas 50% of medium reviews are in Word. Again, I already know it's a medium review, and now I know it's in Word. 40% of the long reviews are in Word. So I already know it's a long review, then this is the probability that it's in Word. Suppose a recent review is randomly selected. Okay, so if I start out, the first thing it looks like they told me was what kind of size this was. So we had short, medium, and long, okay? And that had different probabilities for them. So 0.5, 0.3, and 0.2. Notice when you have a branch in a tree diagram, this is going to sum to 1 for all of those branches. And each of these is the probability of those individual probabilities. So probability of it being a short one, if you just randomly picked one, probability of being medium or long. When you branch out after this, notice we have to know then it's either Word or in LaTeX, which I'm going to call T so it doesn't get confused with the L from long. We have that these are branches off of already knowing that it's short, okay? So these probabilities, specifically, I'm going to give you the first one. I'm going to write it up here so we can see it. That first probability there is the probability that it's a Word document given that it's already known that it's short. So all of these second branches, and if you did third branches, they would be conditional on being on the path that they were already on. So conditional of the prior choices. So this first probability here of being a Word document, given that we were already a short document or short review, is 70%. Now they didn't give you the one for LaTeX or LaTeX, but you can figure it out because this branching group has to add to 1. So it's 0.3. And then the probability of Word given medium length was given to us as 50%, which means LaTeX is also 50%, given that it was already a medium document. And then for long, we know that if it's already long and we know that, it's going to be 40% of those are in Word, and then 60% would have to be in text, okay? Now, when you multiply those branches out, you get what's called the intersection. And I'm going to explain why you get the intersection here. So it's the intersection of short, given, and word, because you did a probability of short, which is a singular event, times the probability of word given short. This is the definition of how to do an intersection if we don't know if the two events are independent or not. So when you have dependent events or you just don't know, this is how you compute your probability of an intersection. It is the probability of the first event and then the probability of the second event given that the first event has already occurred. So just that's a definition for us, okay? So if we multiply those together, this would be 0.35. Whoops. Let me go down. I'm going to write that a little bit smaller. WebAssign doesn't give me a lot of room when I download these to write. So I could go through and do this for each of these. I'm going to just write them out. I'm only going to label a couple of them because I'm looking at the wording of the next question part after we get this done. So this one would be 0.15. I'm going to label this one. This is probability of medium intersect word. I'm going to be talking about word in a minute, and that's 0.15. This one is also 0.15. This one is the probability of long document and word, and that is 0.08. This is 0.2 times 0.4. And then the last one is 0.12. Now, I only focused on the ones that had word because I was already looking ahead at my question, but you could obviously label all of these. This would be short and LaTeX, medium and LaTeX, large and LaTeX intersections. This should sum to 1 as well. So that is 50, 30, and 20. Yeah, that adds up to 1. So that's our total breakdown of our tree. So here's the deal. If you want the probability that something was selected, that the review selected was in Word, and all of our problems here, the only singular probabilities we knew were the size of the document. Well, the cool thing is, if you go through and you have all these conditional probabilities, you can find all of the options that ended in Word, which means that's the probability that I could have selected a Word format without worrying about the size. In other words, we don't care about the size so much. We were saying these are all the ones that ended in Word. So if we add those together, the probability of small intersect word plus the probability of medium intersect word plus the probability of large intersect word. So those are all those ending branch conclusions, those intersections. Then that's going to tell us the probability that someone randomly selected a document and the document was in a Word format, because there was this choice or this choice or this choice. So we're adding. And that turns out to be, so that's 58, so 0.58. Now let's talk about why we need to use Bayes' theorem for part B. It says, if a selected review was submitted in Word format, what are the posterior probabilities? That's the key word right there. Posterior probabilities of it being short, medium, or long. So we already know it's Word. So we're asking for the following probabilities. What's the probability that I have a short document given that it's a Word document? What's the probability that I have a medium document given that it's a Word document? And what's the probability that I have a long document given that it's a Word document? So Bayes' theorem essentially says that, and I'm going to write it specific for our cases, but this would be for all of them, that the formula that we want, so I'm going to do this first one, the probability that it's short given Word, and notice that's nowhere in, I have Word given short, but I don't have short given Word anywhere in my table. So we're saying we're basing this condition off of the probabilities that we got when we added everything up. We knew the end result. We'd already gone through all of our possible options, okay? And we're trying to figure out what's then the prior of that. We have these, we're trying to go backwards, okay? Trying to think of an easier way to explain that. So the way it works is you do the branch that you desire. So the branch we desire is the short with the word ending, right? Okay, because we want to go backwards that way. So we write it as it's the probability that we had word given short times the probability of short. That was the branch that is the desired branch over all possible branches that end in W. So that's going to be probability of word given short times probability of short plus probability of word given medium times probability of medium plus the probability of word given long times probability of long. Okay, but we already know those are those different intersections we came up with, and we have those sums for each of those. So for this first one, the probability that I have a short document in my hand, given that I knew it was a Word document, well, we already know the total of all of those. The denominator adds up to that 0.58 from part A. The specific case we want is the 0.35. So if we take 0.35 and divide it by 0.58, that's going to be 0.603 if we rounded 3 decimal places. So we don't need to write this long formula out for all of the remaining ones because essentially the bottom is going to stay consistent. It's all possible branches that end in word, which we find by multiplying the singular, short, long, or medium ones times their conditionals that it was word given the original. And then we put the desired branching on the top. Okay, so this is going to be probability of medium given word is going to be the branch that ended with medium and word. So that's 0.15 divided by all branches that ended in word. So that's 0.58. So that's going to be 0.259. And then the probability of long, given that it's a Word document, again, 0.58 was all branches ending in word, and the long branch was the 0.08. So that's going to be 0.138 when we divide. So that's a simple version of Bayes' theorem. So hopefully that helps you when you're looking at some. And then our last one for the section 2.3, 2.4 video, just one that I find that is simple, but students will make it harder because we're fixated on a lot of the wording in the problem. So it says a box contains 6 40-watt bulbs. So let me write this down. So we have 6 of the 40 watts. We have 7 of the 60 watts. And we have 5 of the 75 watts. That's a total of, let's see, 12 plus that's 18 bulbs. If bulbs are selected one by one in random order, what is the probability that at least 2 bulbs must be selected to obtain one that is rated 75 watts? Okay, well, that is, so what they're asking for is essentially you're having to pick one of the other bulbs before you pick the 75. So, and that can get really complicated because it's like, well, what if I pick the 40 first versus what I would pick the 60 first? And then, then we'd have to go through, and then a 75. Then we'd have to think, well, this is all kind of almost infinite up to all of the bulbs because you could have all of the 40s picked, all of the 60s picked, and then finally pick a 75 watt. And that would still meet this condition. You had to at least select 2 bulbs before you obtained one that is 75. So why I said this one I wanted to do is because I find that students make it complicated. We can do this really quickly with a complement. So that at least 2 are selected to obtain, just kind of writing what we're going to do, one that is rated 75 watts. If we want to do that, the complement to this would be all cases where a 75 watt is selected first. Okay. So essentially, this ends up being a really simple probability. So 1 minus the probability that we have a 75 watt selected first, which means just selected, is 1 minus, there were 5 out of 18 choices to get a 75 watt bulb. So this would be 1 minus 0.2778, which equals 0.7222. And I believe they asked us to round to 3 decimal places. So 0.722. All right, and that's the end of the 2324 video.